Hello guys, this video is a part of series of videos of the ongoing challenge on LeetCode, which is June Lead Coding Challenge 2020. You can find the link to the complete playlist in the description of the video, where I've added solution along with the explanations for all the challenge problems published till now. So this is week 2, problem number 1, power of 2. So the problem is you are given an integer and you have to write a function to determine whether it's a power of 2 or not. As simple as that. So all the numbers that are of the form 2 to the power 0, 2 to the power 1, 2 to the power 2 and so on should return true, and if there's a number which is having any other factor than 2, then we should return a false for that. Okay, so all these numbers should return a true, and if there's a number which is not a power of 2, we should return a false in that particular case. Okay, so what I'll be showing in this video is, so this is a pretty easy problem. There's not much to this problem that you have to do. So this might be a tutorial which is targeted towards people who are new to programming, or who are just starting their journey to in competitive coding. Okay, so you might find these concepts useful because I'll not be just solving this problem using just one approach, but I'll be using several approaches in order to solve this problem. Okay, so approach number 1 is we just keep dividing the number by 2 until it reaches 1. Okay, so if I say that any number is of the form 2 to the power k, what does that mean? That the only factor that the number is having is 2. So if I just keep dividing this number by 2, so there will be a point where it will reach 1. Okay? And if a number is a 2 to the power, if a number is of the form 2 to the power k, then if I keep dividing this thing by 2, there will be a point when it reaches 1, and there will not be any point in between where it will be equal to any other number. Okay, so for example, consider 16. So if you keep dividing it by 2, you'll have 8, then you'll have 4, then you'll have 2, and then you'll have 1. Okay, consider another number, say 24. If you keep dividing this thing by 2, you'll have 12, and then 6, and then 3. And here you realize that you cannot divide this number by 2. Okay, because this thing becomes an odd number. Okay, so the way we will be implementing the solution is we'll keep dividing the number by 2, and we'll check that if at any point of time this number that we are keep dividing by 2, if that number becomes an odd number, that means that the given number is not of the form 2 to the power k. That's the first implementation that we'll see. Okay, so let's just try to do that. And also one thing to keep in mind, if there is a negative number, then of course a number of the form 2 to the power k cannot be a negative, so we'll just return a false in that particular case. Okay, let's just try to code up the approach 1. So if n is the number, we'll just keep dividing n till n is greater than 1. And if at any point of time we realize that if n is an odd number, so if n mod 2 double equals 1, or I can just simply write if n mod 2, we'll just return false in that particular case, and we'll keep dividing n by 2. Okay, if that is not the case, so we'll exit the while loop only when n becomes equal to 1, and we'll just return a true in that particular time. So let's just try to run this code. Just try to submit this as well. Okay, so this gets accepted, but this is just the approach 1. So I'll be demonstrating you 4 more approaches. Okay, so here you can learn a particular concept known as bit manipulation, which is very useful concept in competitive coding, and we'll learn how numbers are represented in the form in the binary representations using ones and zeros, and we'll see what we can do with that as well. So approach 2 is to count the number of ones in the binary representation of the number. So when I say binary representation of the number, so how is a 4 represented in a computer? So a 4 is represented as in its binary form. So the binary form of 4 is 1 0 0. Okay, a binary form of 8 is 1 0 0 0. And any number which is of the form 2 to the power k, its binary representation will be 1 and then all the other zeros. Okay, so if I tell you one thing to observe a constant which is the count of ones. Okay, so how many ones are there in all these representations? So if you notice clearly, there will be exactly one in all of these representations which are of the form 2 to the power k. Notice that this is not the case in any other number. The reason being something like this. So for example, let's consider the number 24. Okay, sorry, 24. So I can actually break this number as some combination of 2 to the powers. So I can write 24 as 16 plus 8. Okay, now if I consider 8, 8 in its binary representation can be written something like this, and 16 in its binary representation can be written something like this. And if I add these two numbers, I'll get the binary representation of this 11000. And you see, the count of 1 is not 1 here. We have two ones here. Okay, and it is true for any other number which is not 2 to the power, which is not of the form 2 to the power k. Take 3 for example. So 3 can actually be written as 2 plus 1. So this 2 is a power of 2 and then 1 is a power of 2. So what I can do is I can represent this 3 as 1 and 2. And if I add these two numbers, this is the representation that I get for 3. And you can see that the count of 1 here is not 1. Okay, so another observation, we'll be using this thing in order to code up the solution, which is the count of ones in the binary representation of a number is exactly equal to 1. So this is what we'll be doing in the second approach. So how do we do that? So let's just initialize a variable count equals 0, and we'll just keep. So next concept is to actually figure out how do we obtain whether a particular position in a binary representation is corresponding to a 1 or a 0. Okay, so the trick to do that is something like this. For example, if you have this binary number, okay, now if I have to count the number of ones in this, there are several ways to do that. What we'll do is we'll keep shifting this number right by one step, which is the right shift operator that's used in C or C++, and we'll keep checking the number which is present at this particular location. Okay. What we'll be doing is we'll be taking the AND of this number with 1. Okay, so 1 is nothing but this, all zeros and a 1 here. If I take the AND of any number with 1, I'll get a 1 if this digit is a 1, or I'll get a 0 if this digit is not a 1. So what we'll be doing is we'll be taking AND with 1 with the given number every time, and if you obtain a 1, we'll just increment our count, and if you obtain a 0, we don't increment our count. So for example, let's try to run this for this number, which is 101011. I take AND with 1. When I take the AND with 1, so all these things are 0. So we are taking bitwise and this 1 and 1 becomes 1. So you see that when I take AND of this number with 1, that gives me a 1. So that actually makes count as 1, okay, because we have initialized our count as 0. So let's consider the next step where we shift this number to right by 1, which is we do by right shift operator. So the next number becomes 10101 because this 1 will be gone when I right shift it by 1. Okay. Again, if I take AND by 1, this is what it is, and the final AND is going to be 1 again. That's a 1. We again increment our count, so count becomes 2. Again, we shift this number, right shift. So when I do a right shift, it becomes 1010. And if I again take this with AND with 1, and with 1, so this becomes 0. Why? Because all these things are going to be 0, and since I'm having a 0 at this place, so 0 and 1 is going to be 0 again. So I don't increment my count, so count remains 2 here, and you can keep doing this process. So that will actually give you the total number of ones that are there in the binary representation of this number 101011. Okay, so this is what we'll be doing next. So approach 2 is while n is greater than, so you need to also see like till when you have to do this thing. So of course you have to keep doing this thing when, so you have to do this for 1010, then next you have to do this for 101, next you have to do this for 10, next you have to do this for 1, and next if you try to right shift this thing, it becomes a 0. Okay, so this is the point where we have to stop. So we can say that while n is not equal to 0, we just keep doing the right shift operation inside the loop. While n is greater than 0 or while n is not equal to 0, we can have both the cases. We can keep doing the right shift and we can check whether there is a 1 at the rightmost place in the binary representation, and we do that by doing an AND with 1. So what we can do is if n and 1 is equal to 1 is equal to 1, or actually whenever you have these kind of conditions is equal to 1, you can actually ignore that. So if we can just have if n and 1, we just do count plus plus. So n and 1 is going to be 1 if we are having ones at the rightmost place, or in cases like this n and 1 is going to be 0, complete number is going to be 0 if we have a 0 at the rightmost place. So this condition will evaluate to true when n is actually a odd number, if you see, and this will evaluate to false when n is actually an even number. Okay, so the reason being, whenever you have a 0 at the end, that is actually an even number, and whenever you have a 1 at the end, that is actually when you have an odd number. Okay, you can figure that out yourself as well. So that's going to be count plus plus, and I'm going to right shift n by 1. Okay, at the end, I want my count to be 1, so I just return count equals 1. Okay, if you guys are confused with this notation, this is simply if count double equals 1, then return true, or I'll just return false. Now since you can see that count double equals 1 in fact gives you true when count is 1. So if count is 1, then I'm just returning true. Instead, what I can do is I can then just simply return count equals 1. So if count is 1, this thing is going to be 1 equals 1, which is 1, and this thing evaluates to true. If count is not 1, this thing evaluates to false, and I'll be returning a false. Let's just try to submit this code as well. Oops. Uh, okay. So where's the error? Line number 17. While n is not equal to 0. My bad. Sorry. Okay, accepted. So that's approach 2. Uh, there's another approach in C++ that's using the count of the set bits, where you can use a built-in method in C++. Okay, so remember what we were doing? We were trying to count the number of ones that are there in a binary representation of a number. What we can do is C++ actually provides you a really fantastic way which directly returns you the count of the number of ones. I can just accomplish this thing in one line, and I can just say okay. So what is happening here is, so there's a function known as built-in pop count. This actually counts the number of ones in the binary representation of a given number n. So if I'm going to have a total of 1 then I'm going to just return so this is actually very equivalent to the count that we had before. Okay, I'm just returning count double equals 1. So let's just try to submit this as well. This is just a one line code, and let's see. Okay, so this gets accepted as well. Okay, next approach is to actually use bitset in C++. So there's this special data type known as bitset, and bitset actually comes with a method where you can count the number of set bits for a given number. So this is what you do. So this is the same logic that we are doing. We are still have to, so the set bits are this 1 bits. Okay, so bitsets count method actually gives you the flexibility, or gives you the option to actually count the number of set bits, which is to count the number of ones in the binary representation of a number. So what we'll be doing then is, I'll be just declaring a bitset. So if you see, we always have to declare a bitset of a particular size. Okay, if you know, an integer in C++ or C is actually the size of an integer is 4 bytes. 4 bytes is nothing but 32 bits. Okay, so that's what is going to be the dimension of my bitset. So bitset b n. So what I'm doing here is, I'm just declaring this bitset. So this is a special data type in C++. If you're not comfortable with this thing, I would really recommend you to go and refer to CPP reference. I'll give the link to this particular thing in the description, so you can just go and read about it. So this is the way you initialize your bitset. So your bitset is of the number of bits are 32. The variable that we are using is b, and the number with which we are initializing this variable b is n. And what we want is, we want that if b dot count is equal to 1, we should return true, or else we should return false. So again, you would have guessed, I can just directly return b dot count double equals 1. So this thing, if it evaluates to true, that means that the number of set bits in b, or the number of set bits in the binary representation of this number n is 1, or else if it doesn't evaluate to true, that means that this is not 1, this is something else. Let's just try to submit this as well. It gets accepted as well. Approach 4 is the one which I really recommend, and this is something that you should know. This is a special property with the numbers that are actually a power of 2, and this is one of the best approaches in all these cases. Okay, so let's just have a look at what the property is. So we have already seen that all the numbers which are of the power of 2 are of the form 1 followed by some zeros. Okay, so I might be having some zeros, but this is one for sure that after this I'll be having all the zeros, and on the left side also I'll be having just the zeros. We actually don't consider the left part because this is not significant. So this is what the binary representation of a number which is of the form 2 to the power k looks like. Okay, now what happens if I subtract 1? What I'm saying here is, suppose if this is the number, say I just fill these locations with 0 as well. Okay, so the number becomes 0 0 0, and if I just subtract 1 from 2 to the power k, so when I subtract 1, that means that so what happens when you subtract 1 from 4? That becomes a 3. A binary representation of 4 is 1 0 0, and if you subtract 1, so this is equivalent to this. You can just do this. So this 1 0 is actually 2, which actually becomes 1, and then this 1 0. So this 1 0 is 2, 2 minus 1 is 1, this 1, and then 0. So what I'm doing here is the binary subtraction. This is not 10 minus 1. Okay, so just remember that. So 4 minus 1 gives me 3, or you can just simply do that, since this is 1 0 0, and if I just subtract 1, so the number before this is of course going to be 0 1 1. So basic binary stuffs. So the number that we'll obtain is something like this. Okay, now what happens if I AND these two digits and these two numbers bitwise AND? So of course this 1 and 0 is going to become 0, and since this all are zeros, so if I take AND, so I'll be obtaining all the zeros here. Okay, so one property to notice here is, if I take the AND of 2 to the power k with 2 to the power k minus 1, what I obtain is a 0, because this thing, if you see, is a 0. Okay, but is this the only property that the number of the form 2 to the power k exhibits? So let's just try to analyze that as well. If there is a number which is not of the form 2 to the power k, then at least we are going to have two ones in the binary representation of it, right? So the number might look something like this, and so on, but at least we'll be having two ones. So the other one can appear anywhere, but at least we'll be having two ones. This is for sure. Okay, now what happens if I subtract 1 from here? What will happen is, so we'll again do the carry, and we'll do the carry from this side. So this thing will become a 0, this thing becomes a 2, this thing becomes a 1, this thing becomes a 2. So 2 minus 1 is 1, this thing is again a 1, this thing is 0. And if you notice this part, this whole part here, this thing is not affected at all. So we'll be just directly copying all the values which are written up there, which is 0 0 1 0 1, and so on. Okay, now what happened precisely is, since the number was 10000100, and this was the place where we encountered the first one from the right side, that actually got changed to a 0, and then all the numbers after it got changed to 1. Okay, now if I take AND of this number and this number, that is definitely not going to give me a 0. Why? Because you can see that 1 and 1 is 1, and if I have a 1 here, no matter what I put here, the number is not going to be a 0. Okay, so what you can conclude is, if there is a number which is of the form 2 to the power k, this property always holds, and this property only holds when the number is of the form 2 to the power k, which is, if you subtract 1 from the number, and if you take the pointwise AND of the number and its one subtracted form, if the number is of the form 2 to the power k, which is if the number is a power of 2, you are going to get a 0 when you AND these two quantities. So that's what the implementation is. Along with this, I'll also show you one more thing which might not be very usual, and many of you might have done this mistake. So personally, I have made these mistakes many times. So I'll first show you the mistake that I usually did before, then I'll come to the final solution. So of course, the thing that we need to do here is, so if n and other number is n minus 1, if that is equal to 0, so I just need to return true. Why? Because this is only the case when the number is power of 2. Okay, else I can then just return false. Okay, that is the thing. Let's just try to submit this code and let's just see what happens. So I'm getting a wrong answer. Our logic was correct, but still I'm getting a wrong answer. And if you see, the input is 2. So let's just try to run this on input 2. So 2 is this. And if I subtract 1 from this, then it becomes this. So this is 2, this is 1. And if I take AND of both of these quantities, this is definitely going to become a 0. So this means that and n minus 1 definitely evaluates to 0. But why am I not getting the correct answer? So the reason here is that it's because of the precedence of this and equals to. So when you write something like this equality gets evaluated before taking the and. So that is why what you need to do is you need to put this whole thing in parenthesis so that this thing gets evaluated first, which is n and n minus 1, and then only this equality evaluates. So it has something to do with the precedence order that's there in C++. Let's just try to submit this code and let's see what happens. Okay, so that is accepted, and this particular method is something that is useful in many of the other problems as well. So what I'll be doing is, in the description I'll be sharing more problems on bit manipulation that you can go and practice. And just remember, this approach can be useful. So if you're really new to coding world, and if you have not done a lot of practice on bit manipulation is actually a very good topic, and you should definitely try out your hands on that. And yeah, thanks for watching. So we have discussed a total of 5 approaches in order to solve this problem. Let me know in the comment section which approach you used to solve this problem. And yeah, thanks for watching. If you have any suggestions, if you want me to make separate videos on bit manipulation or other similar topics, do let me know in the comment section as well. Thanks for watching.